Good morning. So you're getting older, right? And you deal with maybe some immature people around you, and it's frustrating. You can't wait to maybe get a little older into the workplace where you don't have to deal with uncommunicative and petulant people. I've had a tough morning. The egos around here, you have to very gently coax them one direction or the other. Anyway, can't go into detail about it. I went to Roanoke with my wife this weekend, and we ran a 5K Saturday morning, and it literally snowed, like during the 5K. So that kind of was cold. That wasn't too much fun. Okay, so let's see where we're at. I'm really happy with what we got done Friday. We have, let's see, we did olive radicals, which puts us in a really good spot. So we're going to be starting on Chapter 9 today. Our exam is when? Next week. It's next Wednesday, right? The 20th. That's in 9 days. I'm going to put out an office hour workshop schedule for basically until exam 3. I'll put that out today. Today, I have office hours from 2:30 to 3:30 in room 2018. So that's today's office hours, and then I'll get a schedule out soon after class. There's homework due. When is that due? It's due on Wednesday, right? So we have that coming up. I'll check and make sure. We should be in a good spot to have all that material done. Okay. So let's see. We're going to start with Chapter 9. And so the book does this all in one chapter. I think that's kind of nuts to do this much material in one chapter. We're going to really split it up quite a bit. And so Chapter 9, according to the book, is substitution and elimination. But that's a lot of topic. And so what we're going to say is that substitution is definitely going to be on exam 3. Without a doubt. Elimination, I don't really know. If it is on exam 3, just not much of it will be. So certainly all of substitution I think will be good, but here, elimination, we're going to go with a question mark. That said, if we don't get to elimination, we are going to spend plenty of time talking about it after the exam, so we covered up the finals, so we are going to get through it for sure. And really, these are these topics are very canonical Orgo 1 topics, so this is something that everyone learns in their Orgo 1 careers at some point. Okay, so I'm going to do things, I think, a bit out of order from what the book does. So we're just going to start with intro. And so we learned last class that what we can do, for a long time we hadn't really learned anything that we could do with alkanes, but we learned last class that we can react them with radicals. And so we have, let's see, we can take propane, and then some sort of halogen. In fact, we learned that in this reaction we can really only use chlorine or bromine because fluorine is way too exothermic and iodine is actually endothermic. So either bromine and chlorine. And what else do we have to add for any reaction to take place? Yeah, we had to add light. So we have some light in there. And so what we end up with is an alkyl halide. So we're going to have our halogen add to one of these carbons. And so we've got two possibilities in this case, a primary and a secondary. What's going to be the major product? Definitely the secondary, and that's because this mechanism is going to go through a radical, and so we know that secondary radicals are more stable than primary. Okay, so we learned this last week, and so what we've got here is an alkyl halide. Good for us. Useful things. All right, so this is very useful. And they're going to take a fairly prominent role when we talk about substitution and elimination reactions in this chapter. All right, and really, I think that elimination will probably take us through the Monday of the last week of classes, which we are really close to. We're like 3.5 weeks from being done. That's a little nuts, right? So, all right, so that's coming up really quickly, but that's also good because that means May's going to be here and we can finally settle down and relax after we take the exam. Okay, so that was last class. We learned how to make alkyl halides. So now we're going to do something different. So let's take that same alkyl halide. All right, so there's our alkyl halide. And essentially what we've got is now a functional group handle. See all along we've said alkanes aren't very reactive, and we've seen that we've got to treat them to some interesting conditions to make them reactive. We have to create radicals and use light. But now we've got halides, and an alkyl halide is much more reactive, and in reality we have options. There's different types of reactions that we can do once we've formed an alkyl halide. In reality, there's probably thousands of different reactions that have been developed for alkyl halides. We're going to focus in on 2 of them. And so the first one is going to be our substitution reaction. So really this is going to be a little bit of an introduction to the difference between substitution and elimination, and then we're just going to kick elimination to the curb for like a week. Alright, so substitution requires a nucleophile. So a nucleophile has to have a lone pair, and so we'll stick a negative charge on there. That'll make it even more nucleophilic. And so what we end up with is exactly what it sounds like. We're going to substitute our X with our nucleophile. So we end up with a product over here where we've got our nucleophile added in, and then we're going to have our X minus that has basically been displaced. It has been substituted for. Alright, so this is going to be this week is we're mainly going to talk about all these types of possibilities for substitution reactions, and then later on, go ahead and finish our arrows here. Later on we're going to talk about elimination reactions. And so in an elimination reaction, we don't necessarily use what we refer to as a nucleophile. And so here we're going to use a B. What does that stand for? Base. That's a base. And so in a lot of cases, and this is what we're going to talk about down the road after exam 3, is the fact that, well, we see that a nucleophile has a lone pair, and a base has a lone pair. And so what we can have is one molecule that can qualify as both a nucleophile or a base. And so depending on the characteristics of that molecule, it's going to react as one or the other. And so that's going to be part of what we do, is figure out, well, what reaction is going to take place given a certain set of conditions that we see. All right, so for an elimination reaction, basically, it's going to be the reverse of an electrophilic addition reaction. So what we end up with is an alkene plus HB. All right, and so this should look somewhat familiar to you because we've learned how we can go from this to this. How do we do that? So that's just a Markovnikov addition of an acid to an alkene, right? And so essentially, when we talk about elimination, what we're doing is the reverse of an electrophilic addition. So we saw in the electrophilic addition chapter, we can take this alkene, we get the Markovnikov addition of X, and so essentially an elimination reaction is the backwards reaction of that. So if we treat it with a base, we can go the other direction. All right, so we've talked a little bit about naming alkyl halides, but I don't think we've really put anything down on paper. So let's go ahead and briefly do that. So we'll say naming alkyl halides. And we're not really going to do anything special, so we're just going to treat X as any substituent. And so if we see, say, a fluorine as a substituent, what do we call the substituent? Fluoro, right? If we see a chlorine, it's chloro, bromo, iodo. It's just, that's pretty much it. That's all we need to really remember. And so for example, what we could have is a molecule that looks, say, like this. We'll put a couple of methyl groups there. All right, so we've got our molecule, and of course, we want to make sure that we pick out the longest chain. And so what is the longest chain here? How many carbons? Should be 7 carbons, right? So we have 2 options. We can number left to right or right to left. And so which way, according to all the rules we've learned up to this point, are we going to number? Yes, we're going to treat bromine as any substituent, and that means we're going to number such that we encounter a substituent first, right? And so if we count left to right, we see we're going to hit a methyl group at carbon 2. If we count right to left, we're going to hit that bromine at carbon 3. And so what we want to make sure that we're doing is numbering left to right so that we can give that methyl the number 2. All right, so we've got a carbon chain that is 7 carbons long. What's our root? Yep, so that's going to be heptane. And then let's see, do we have any stereochemistry? Yeah, we do. So we'll say we've got 1, 2, and 3. And so our hydrogen's in the back, so is that R or S? That's definitely R. And so what we'll call this guy is 5R. And so we put our stereochemistry first, just in parentheses like we've been doing. And then we think about our two possibilities for substitution. So we've got a 5-bromo, and then we're going to have a 2,3,3-trimethyl. And so in our name, which is going to come first? Why? Alphabetical, right? And so it's just the same exact rules we've learned. So we'll say that we've got 5-bromo, 2,3,3 trimethylheptane. And we're good. All right, so there's not really anything new to naming this. We just need to remember what we call our halogen substituents. Same rules apply. Okay, so this will lead us to Roman numeral number 2. And so in Roman numeral number 2, we've seen an introduction to substitution versus elimination. Now, like I said, we're going to kick elimination to the curb for quite a while. And so we're going to focus in on substitution. And we'll just call this substitution. Subtitle, intro. All right, so we'll talk a little more about what substitution really is. So first we can define it. So by definition, a substitution reaction we could consider as the exchange of one sigma bond for another sigma bond. So basically, we're going to break a sigma bond, we're going to form a sigma bond, we're going to end up with a carbon that is still connected to 4 things, and so essentially we're just going to replace one substituent with another. And so for example, what we're going to have is we have, say, our nucleophile, and then, actually, let's say that a substitution reaction requires a few things. And so the first thing that a substitution reaction requires is going to be a nucleophile. All right, so that's fine. We'll draw an example reaction over here. So we've got our nucleophile with its lone pair. It doesn't always have to have a negative charge. Sometimes it does, sometimes it doesn't. We'll see how that impacts reactivity down the road. But for now, it can be either way. And so we have a nucleophile, and we're calling it that. We're reacting it with something. What are we reacting it with? An electrophile, right? And so a substitution reaction also requires an electrophile. And so when we draw an electrophile, what that's going to look like is we're going to have some group of R stuff, right? Some CH stuff. And then we're going to have what we refer to as an LG. All right, what does that look like? So we're going to have, we'll just put a methyl and then an LG. And so all of this stuff we're going to refer to as our electrophile. All right, so we've got our nucleophile, and we've got our electrophile. So we can dive a little deeper into our electrophile, and we see that it's got an LG. And so that's kind of where our theme song for the day, John Denver was leaving on a jet plane. And so what we're going to have is an LG that stands for what? Anybody? All right, it's going to be a leaving group. And it's exactly what it sounds like. It's going to be some group that's going to be displaced. Now, in a lot of cases, we'll see halogens are used, and halogens certainly make great leaving groups, but those aren't the only groups that can be leaving groups, and we'll learn more down the road. We'll probably stick with halogens for the foreseeable future until we learn some more. All right, so a leaving group. A few things about a leaving group. It must be stable by itself. All right, so in our reaction, what's going to happen is we're going to form a new bond between our nucleophile and our methyl group, and then we're going to end up with a leaving group that is on its own, so it can take a negative charge. And so, for example, it could be a halogen that is our leaving group, and so in that case, we would end up with a halogen and a negative charge there. Now, what do we know about the stability of a negatively charged halide by itself? Is it pretty stable? It's definitely pretty stable, right? That's what makes a strong acid a strong acid. So we think about our halogen acids, so something like HCl. We know it's a strong acid, and of course, we learned early on in class that acidity strength is based on the stability of the conjugate. And so the conjugate of HCl is Cl minus, incredibly stable, and that's why HCl ends up being a strong acid. So that's the reason that we end up seeing halogens act as such good leaving groups. All right, so we can also add that leaving groups are often the conjugate of a strong acid. And that's just because the conjugates of strong acids are so stable off on their own, right? So they're happy to be lost in an acid-base reaction. They're also happy to be lost in a substitution reaction because they end up just going off and doing their own thing. And so what we find is that halogens make great leaving groups. Which halogen do you think maybe doesn't make a great leaving group? Fluorine. Why? Well, HF is a weak acid, right? And so in that case, we don't have the conjugate of a strong acid. So we'll say halogens, except for lonely fluorine, make great leaving groups. All right, so that's why our alkyl halides are so important, is because we're able to begin now with substrates that have good leaving groups, and so we can connect the dots and make new products. All right, so we haven't talked much about the mechanism, and so we've got some possibilities for the mechanism of a substitution reaction. So the next part we will title mechanism, with a question mark. And then what we find is that there are ultimately going to be multiple possibilities. And we're going to spend a pretty significant amount of time talking about these multiple possibilities and what kind of mechanisms our substitution reactions can go through. It ends up being pretty important. All right, so for one thing, the first case we can think about is the idea of a concerted mechanism. Now when we talk, and I know I've used this a little bit in Orgo 1 this semester, what does concerted mean as it applies to a reaction mechanism? Everything happens at once. Everything happens simultaneously, and that's exactly what it means here. All right, so when we talk about a concerted mechanism, we're just saying that everything is simultaneous. All right, so if everything is simultaneous, we know in a substitution reaction we're forming a new bond and we're breaking a bond, so that means we're just going to do it all at the same time. So what we have is our nucleophile with our electrophile. So we know, all right, so we're going to show an arrow going from our nucleophile to our methyl group. Where are we going to start our arrow? At the electrons. We're always going to start at electrons, right? Nobody is going to start an arrow away from electrons on exam 3. All right, so we're going to break the methyl leaving group bond. So where do we start that arrow? At the electrons of the sigma bond. And so those are going to go right back and be pushed onto the leaving group. So in this case, what we're doing is we form our new bond. That's the nucleophile methyl bond here. And at the same time, we have our leaving group going its own way. And so one step happens at the same time. All right, so alternatively from a concerted mechanism, we could have multiple steps. And so let's see what our possibilities are here. So we'll refer to this as a stepwise type mechanism. And so I think that pretty much speaks for itself. It's going to be mechanisms where there are multiple steps. And so let's think about the possibilities. So again, we can start with nucleophile. We have the same electrophile. And so let's see what happens. Let's try to form our bond first in its own step. And so what we get in this case is going to be something that looks like this. Now, who has any problems with that? What's the problem? Texas carbon, right? We're breaking the octet rule. And so is this going to be a possibility? This is definitely not a possibility here. All right, so this is no good. We're never going to form our bond in its own first step. But we have two steps, right? We have a bond. Is there a Tor out there? All right. We have a bond. We have a bond forming and a bond breaking. So we could imagine doing our bond breaking step first. So let's see what that result is. All right. So here we know this is no good. Breaks octet rule. Everyone remembers why we call it a Texas carbon, right? Because things are bigger in Texas. All right, so let's think about maybe breaking our bond first. So we have our methyl leaving group. So we're just going to say, bam, this happens. It just happens. All right, so in this case, we're going to end up with a carbocation plus our leaving group. And is there anything wrong with this picture? Are we breaking any rules? Can we have carbocations? Yeah, that's perfectly fine, and so we're okay at this point. All right, so we're going to have one step where we're breaking a bond. We then need to have our step where we're going to form a bond. And so then we can imagine our nucleophile basically snapping in, right? This is going to be a this is going to be a very fast reaction because we've got a negatively charged nucleophile, a positively charged open shell carbocation. So as soon as we form our carbocation, we can imagine these two things snapping together. We're going to end up with the same product. We end up with a new nucleophile methyl bond along with our leaving group. All right, so really we're going to have two possibilities. We're going to call this, I guess, possibility 1 and this possibility 2. And we're going to spend a pretty good amount of time talking about these two different possibilities because they both happen. They differ in one important, significant way. And so we'll say it's a star. The only difference in the mechanisms is the timing. So that's what we want to focus on as we go. It's the timing of our steps. The steps can either all happen at the same time or they can happen at different times. So let's see, let's focus in on the concerted mechanism first. So we'll say Roman numeral number 3, we have the concerted mechanism. And so the concerted mechanism gets a special name. Does anyone know the special name of a concerted substitution reaction? Starts with an S. S, all right, so we get a big S, and then we're going to have an uppercase but little n, and then we get a 2. And so from here on, if you ever hear SN2, you know you need to remember that we're talking about a concerted mechanism. That is kind of the defining thing about an SN2 reaction. So we'll talk about how it gets that name. In fact, that's the first thing we're going to talk about. Why do we call it SN2? All right, so we'll say letter A. We're going to talk about the kinetics. So I think the book probably mentions this. I think it was like the 30s that maybe it was figured out. So for a long time, people knew that substitutions could take place, but they didn't know mechanistically how it was going. It took a while. I think it was like right before World War II that we really figured out what the mechanisms were and what was operating given a certain set of conditions. And so when we think about our SN2 concerted mechanism, all right, so we're going to draw it a lot. So we've got our nucleophile. And so now our electrophile, we're going to get a little more specific. So we'll draw this chain right here, and we'll just stick a leaving group on there. So why does this reaction happen in the first place? Well, in a lot of cases, our leaving group is a halogen, and so that's electronegative. And so what we end up seeing is a dipole that goes in this direction, right? So we're going to have a halogen that's stealing electron density from the carbon it's attached to. And so over here, we've got a partial negative. And over here, we've got a partial positive. And so now it should make sense that our nucleophile, right, we have a nucleophile that's attracted to positive charge. So it's definitely going to want to snap right into there to that carbon with a positive charge. And so that's what we see. Start our arrow at the electrons. And then as the incoming bond is forming, the other bond is going to be breaking. And so what we see is this is a one-step reaction. And so because it's a one-step reaction, this only step is going to be our RDS. What's our RDS? It's our rate determining step. And so the rate determining step is going to have a little bit more importance than we've seen in the past. All right, so this is our rate determining step. And so our substrate stays the same. We've still got the same carbon. Now the only difference is we've swapped in our nucleophile to where the leaving group was. And so now the leaving group is out on its own like this. All right, so if we're going to do this reaction, and remember, the rate determining step is the step that determines how fast our reaction goes. So there's only one step, so it's pretty easy to see that in our rate determining step, what has to happen is we have our electrophile floating around in solvent, we've got our nucleophile floating around in solvent, and at some point they're going to have to collide, right? That's the only way that we're going to kick off this reaction. And so we can say with certainty that the nucleophile, what is the E plus? Yeah, that's just shorthand for electrophile. All right, so the nucleophile and the electrophile must collide. And so since they must collide and there's two different things going on in that collision, or at least there's two different molecules participating in the collision, we refer to it as a bimolecular process. All right, so we've got to have two different molecules that are colliding, and so that's going to affect the kinetics. If we were going to determine a rate law for this reaction, we could say that the rate is equal to little k. What's little k? Yeah, so that's going to be some rate constant that is unique to the electrophile and the nucleophile combination. We're not going to worry about what the rate constants are. It's just some number that is unique to each given reaction. And so it's the ultimate rate of this reaction is going to be the rate constant times the concentration of our nucleophile, and also multiplied by the concentration of our electrophile. And so how many different molecules do we have here in our rate equation? We have two types, right? So we have two types of molecules. That's what our biomolecular process is saying. And so ultimately, when we give this thing a name, all right, so we call it an SN2 reaction. Where does the S come from? Yeah, that's pretty straightforward. What about the N? Nucleophilic. So we're undergoing a nucleophilic substitution. What's the 2? Bimolecular. And so that's going to be the big key difference between the stepwise reaction that we talk about maybe at the end of today's class, more likely on Wednesday. Okay, so that's how we get to our name SN2. It's just a nucleophilic substitution that is going through a bimolecular process. Next up, letter B. We're going to talk about the stereochemistry. And this is pretty important because we see different stereoselectivity based on whether it's a concerted mechanism in SN2 or the stepwise mechanism that we'll later learn about. All right, so let's come up with a more realistic example. Let's say that we have an ethyl group. Over here we'll have a bromine. On a wedge we'll put a proton, and on a dash we'll put a methyl. All right, do we have a stereocenter? Sure. All right, so the stereocenter here, we'd say we've got 1, 2, 3. So ultimately our hydrogen is 4, and so that means it's coming out this way. So if we use our left hand with our thumb towards us, we can rotate 1, 2, 3. So is that going to be R or S? Definitely S. So we've got an S stereocenter here. And then we need a nucleophile. So our nucleophile here is we're going to use SH. And so SH is very similar to OH, which means it's going to have what kind of charge? Yeah, it's going to have a minus charge for the same reason that OH has a minus charge. All right, so we've got SH, and we're going to learn that SH is a really, really awesome nucleophile for substitution reactions. And then we have an electrophile, and it does have a leaving group, so we should be good to go. Now, there are two possibilities. All right, so one thing we can do is we could start with our arrows at a lone pair, and we could draw in from the same side as our bromine. All right, so we refer to that as a front side attack. Now, we've been saying for a while that whenever we're going to do a displacement reaction, we can't undergo a front side attack. Is this a displacement that we're ultimately trying to carry out? Sure, right? So we're going to have some nucleophile that's coming in and it's displacing the leaving group. It's pushing something off. And so if that's the case, can we do a front side attack? No way. Definitely not. And so a front side attack is not possible. And if you want to think about why that would be, well, think about what's going on in this reaction. So we've got electrons involved in this carbon-bromine sigma bond, and so that bond's beginning to break, right? So we have a little bit of negative charge developing right here. Well, our sulfur is a nucleophile, right? It's attracted to positive charge, and so it's not going to want to come in as the same side where we already have electron density here. So that leaves one other possibility, not a front side attack, but a backside attack, and so what we have to do is going to be a backside attack where we approach our carbon from 180 degrees of our leaving group and undergo our displacement. So we can say that backside attack is necessary. All right, so definitely we don't want to undergo a front side attack. Don't do that. That's bad. Bad. All right, so let's think about what happens. So we're having our nucleophile come in from the left side, and our bromine is getting pushed off to the right side. but we've got some innocent bystanders, right? We've got the ethyl group and the hydrogen and the methyl. And so if we're forming a new bond here, these other substituents, the methyl, the hydrogen, and the ethyl, they're going to get pushed. And so what direction are they going to get pushed? They're going to get pushed to the right? Because what we're essentially forming is a new bond that looks like this. And so we know if we have a bond in the plane right here, we're going to have everything going the other direction. And so essentially what happens is our ethyl group has been pushed that way. It's still in the plane, and in fact, if we've got something on a wedge or a dash, it's going to stay on a wedge or a dash. So our proton, which was on the left side, or at least slightly to the left side and on a wedge, now it's going to be slightly to the right side and on a wedge. And our methyl group, which was on a dash, has been pushed to that side as well. All right, so let's think about the stereochemistry. We've got 1, 2, 3, 4. And so in this case, let's see, our thumb comes towards us. With our right hand now, we can curl 1, 2, 3. So is it R or S? It is R. All right, so this is one of the key defining things about an SN2 reaction is that we're always going to recover what we refer to as the inversion product. What we're finding is that the 3 innocent bystanding substituents over here, well, they're just going to get pushed to the other side by our incoming nucleophile. And that works because what was over here, our bromine, has vacated the premises, right? So now there's lots of room over that side, so they're happy to be pushed over there. In effect, we end up with the inversion product. All right, so really important question about this inversion product. Does RS always change to the other label? We're going to make a note about this. This is pretty important. So, note. I'm going to spoil it for you. RS does not always change. Why is that? Okay, so we've looked back up here and we see that our leaving group, we gave number 1 in terms of priority. And then our incoming nucleophile, we also gave number 1. And that's just following our stereochemistry prioritization rules. But is that necessarily always going to be the case? You know, our nucleophile could come in, it could end up as number 3. So what that means is that we're not always going to go from S to R when we have an inversion product. We could get the inversion product, but keep the same label because we've essentially renumbered all of our substituents on our stereo center. So we want to make sure that we understand, all right, so it does not change, or it doesn't always change. And so we say Y above the nucleophile and leaving group are both 1, but that's not always the case. And so this is a very easy exam question for me to give you. I'll even give you the stereochemistry here, and then ask you for the stereo label here. And so in some cases it will be R, in some cases it will be S. It will still have undergone inversion, but what you're going to have to do every time is go ahead, reprioritize, and then determine the R or S label. All right, so don't just assume that because we've gone through an SN2 mechanism that we've gone from R to S or S to R. We maybe have not. Yeah?
Is it always going to react with chiral 7?
No, it can react with with just a CH2 group as well. And in that case, you're still getting inversion, right? You're still going to have those groups pushed to the other side, but we aren't able to assign it a stereo label. But mechanistically, we still have to push the groups away. We still have to undergo a backside attack. Yeah, that's a good question. All right, so let's now draw a totally clear picture of what's going on in an SN2 reaction. All right, so we'll use the same thing. We'll use our HS. And so we'll use the same electrophile as before. All right, so we notice that this is an SN2 reaction. We're going to undergo a concerted mechanism that looks like this. Now what we want to do is think about what does our transition state look like. We haven't drawn a transition state in a while. And so to indicate a transition state, we draw brackets, and then what else do we have to put? we have to put our little double dagger, right? So we put that at the upper right-hand corner. That's signifying that we're drawing now a transition state. And so since everything's happening at the same time, we're going to show our bond forming. And so how do we show a developing bond in a transition state? Yeah, we use dots. And so here, what we're showing is our new bond forming. Now we know that in this reaction, our innocent bystanders, the proton, the methyl, and the ethyl, they're getting pushed left to right. Now right in the middle, are they going to be favoring one side or the other? You know, they're in the process of getting pushed. And so in the transition state, at the very top of our mountain peak, they're going to be right in the middle. And so what we show is the ethyl group is in the process of being pushed, but at this point it's just straight down. And so likewise for our proton and our methyl group. They're going to be just about as straight up as possible that we can draw them. They're still going to stay on their wedge and their dash. They're just being pushed. And so finally we have our carbon-bromine bond breaking. How do we indicate a breaking bond in a transition state? Yeah, dots again. We use the same thing. So now we've got our breaking bromine bond. And what we can do is we can start talking about how charge is changing or developing as we're in our transition state. And so we'll go ahead and draw our product. So what we've got is our inversion product. That looks like this, plus our bromine. And so think about where we're at in the middle. So over here on the far left with our sulfur, we've got a negative charge. And so ultimately from the beginning, we've got a negative charge. We end up as a neutral sulfur. And so in the middle, do we have a full negative charge? No, we don't, right? Because we're basically losing our negative charge, but we've still got some charge. And so we can indicate that with a partial negative right on our sulfur. So if we're forming a new charge, or in this case, we're breaking or we're losing a charge, we show it in the process of being lost. And so we're also forming a charge on our bromine, right? So we've got a neutral bromine on the left side, and so then we've got a negatively charged bromine on the right side. And so we do the same exact thing. We say, all right, there's a partial negative there, because essentially what's happening is we're transferring our negative charge from the sulfur over to this bromine. And so right in the middle, they're both going to have an equal amount, but it's not going to be a full negative charge. It's going to be a partial negative charge. Okay. So that's our transition state for an SN2 reaction. Next, we will talk about structure versus rate. And so we're drawing this transition state for a reason, and we're about to see why. All right, so if we take a closer look at this transition state, all right, typically when we see an sp3 hybridized carbon, it's connected to how many things? It's connected to 4 things, right? Well, here, in this transition state, how many things is it connected to? 5, right? Now, 2 of the bonds aren't full bonds, they're partial bonds, but it's still connected to essentially 5 things. And so one defining thing about the transition state of an SN2 reaction is that it is very crowded. And that's going to have a big effect. So what we can say is that the transition state of an SN2 reaction is very crowded. And it's very crowded because ultimately we have 5 bonds. Not 5 full bonds, but we have at least 2 partial bonds. And so we've got a lot more stuff than we're used to being in there around our carbon center. All right, so this now we should be able to draw an energy diagram. So knowing that it's a one-step reaction, we'll have reaction, progression, we'll have energy. So on the left side, we'll have our starting material. So we'll show this as a downhill reaction. So we'll put our product right there. And so in the middle, of course, we're going to have our transition state energy. And is that going to be higher or lower than our starting material? Definitely higher, right? Because it's crowded. We're having to stuff 5 things around our carbon. That's going to be a lot of steric strain, right? So that costs a lot of energy. And so we find that the path from going to from our starting material to our product is going to be uphill. And so here what we've got is our transition state. And so ultimately, it's this energy difference that we refer to as what? Yep, so that's our activation energy. And since it's our only step, this is also going to be our rate determining step, as we've seen. So when we talk about the kinetics of our reaction, how fast is this thing going to go? ultimately it's going to be dependent on this energy difference between the starting material and the transition state energy. Unfortunately, there's a really easy trend that we can help keep track of when it comes to our transition state energy. So, what we can do is we can say the stability of our transition state is determined, or well, we'll say the stability of the transition state determines the reaction rate, since that is our rate determining step. And so we'll all say that the stability of our transition state is determined by crowdedness. I don't know if that's a word, but we're going to use it if it isn't. And so it's all about the crowdedness, right? Because if we have a very crowded transition state, that's going to be very high in energy. If we don't have a very crowded transition state, that's going to be very low in energy. And so what we can do is we can consider a real reaction with some different electrophiles and see how the reaction rate changes. So what we shall do is we will consider the following reaction. All right, so we're going to keep going with our SH nucleophile. And in this case, we're just going to draw a generic alkyl bromide. So we'll just say RBH. That's what we're going to change, and we'll see what happens when we change to the reaction rate. So our product will end up as RSH, and then we'll have Br minus. Okay, so we're going to draw a table. And so on the left-hand side, we're going to have our substrate or our electrophile, RBr. So we're going to start out with methyl bromide, and then we'll draw, let's see, we'll draw this one. We'll draw this one, and then finally, we'll draw this one. And so what's changing as we go from substrate to substrate here? Yeah, it's going to be substitution of our carbon, right? So when we determine what type of alkyl halide we've got, what we do is we look at the carbon it's connected to, and then that's how we determine our substitution. So at the top, we just have a methyl carbon, or a methyl alkyl halide. As we go down one, all right, the bromine's connected to this carbon, and so what type of carbon is that? That's a primary, right? And so we'd say this is a primary alkyl halide. As we go down, what's the next one? Secondary and then tertiary, right? Almost by chance, we have a trend. Okay, so we're becoming essentially, all right, let's think about crowdedness. All right, what's going to be the least crowded of these four? It's going to be the methyl, right? Because the carbon in this case is just surrounded by hydrogens, and hydrogens are tiny. So here we have the least crowded, which means down here when we have our tertiary example, we're going to have our most crowded. And so finally what we can do is we can add in a column for relative rate. And so what do you think is going to be the fastest? Is it going to be the least crowded or the most crowded? We would expect it to probably be the least crowded, right? Because that's going to have the lowest transition state energy. That's going to be the easiest 5-membered transition state to form. And so what we see for the methyl is a relative rate of about 1200. If we increase the substitution by 1 and we go up to the primary alkyl bromide, we see that we have a relative rate of 40. And so it's a pretty significant increase in rate when we go from primary to methyl. The secondary, we end up with just a rate of 1. And so unfortunately, when we try to do this with a tertiary alkyl halide, nothing is detected. And so this is actually a pretty general rule in almost all cases, and certainly in all cases in Chem 206, tertiary alkyl halides, no SN2. They're just too crowded. It's too high energy to go through that 5-membered transition state with a tertiary alkyl halide. All right, so we can compare these things on a reaction diagram. And so what we'll do, I'll color code. So we'll call this one, we'll call our methyl red, our primary blue, and our secondary green. So we'll show an energy diagram. And so the starting materials and the products here are pretty much the same energy level. So we've got reaction, progression. So here we'll have starting material, here we'll have products. And so let's think, for all the transition states, for the methyl, the primary, the secondary, what's going to be the lowest in energy? Should definitely be the methyl, right? Because it's the least crowded. And so that's what we're going to see. So here we'll put our methyl. And then we're going to have our primary. And so our primary is a little more crowded, which puts it a little higher in energy. And so our primary comes up, I don't know, say to right here. And then we have our secondary, which is going to be even higher in energy. And so the different reaction pathways, considering on the substitution of our electrophile, well, our methyl is going to be the fastest reaction. And again, it's going to be because our rate determining step, the energy difference right here, is just this line. Whereas if we were to go through it using a primary alkyl halide, we'd have to climb further up the hill, which is going to slow our reaction down quite a bit, because our activation energy is now quite a bit bigger. And then finally, if we've got a secondary, we've got to climb way up the hill. We have a massive activation energy, and so we see a very, very big difference between those reaction rates. And then for tertiary, basically tertiary is off the map. The tertiary transition state is so high in energy that we just don't even consider it. No matter what we do, we don't see any product ever form. The reaction could happen, but it's just so slow that we say that it doesn't. All right, so we're just going to title the next section really quickly, and then we'll call it a day. So this will be Roman numeral number 4, which we're going to do for the stepwise mechanism. And so our concerted mechanism we're now referring to as SN2. What do we call our stepwise mechanism? That's going to be SN1. So we're going to do the same exact process with SN1 as we did with SN2 today. We'll talk about the 3 categories of stuff. So that'll take probably about half an hour on Wednesday, and then the rest of Wednesday and Friday, maybe some on Monday, what we're going to do is start talking about the different types of conditions we can have and see how we can figure out whether or not SN2 is going to happen or SN1 is going to happen. We've seen that stereochemically SN2 is selective. We'll see what happens with SN1 and how it makes a difference. Again, office hours today, 2:30 to 3:30.